So the heat curve and phase change diagrams notes here. These here are heating or cooling curves. Okay, they're diagrams showing the temperature change over time for a substance as it goes through phase changes. So what I'm going to do, and just so you know, like, I'm going to put up a copy on Classroom of these that are the highlighted that I'm doing. So if you want to look later at the highlighting, if you don't have highlighters with you but you want to do it later or something like that, I'll have a copy that you can go back and look at. Okay. So if we look at this temperature here on the side, as you go up, the temperature would be higher. They don't actually have this. This isn't marked with actual temperatures. If you look at the homework that I handed out, like that one does have actual temperature markings on the side here. Okay, but generically, like obviously, the higher up you go, the higher the temperature is. The lower you go, the lower it is. And then time is the x-axis here from left to right. So what I'm going to do is highlight the portion of the line and then highlight the letter and the stuff that goes with that. So for example, this portion of the line right here, that portion goes with the A. It is a solid. Okay? So that portion of the line represents the substance when it's a solid. All right, now if we look at this and we look at this line, what is happening to the substance as time goes on temperature-wise? As we go along this line, what is happening to the temperature?
Warming up.
Yeah, it's warming up. It's increasing, right? Okay, so the temperature is increasing. Now, oh, and by the way, some of the stuff that I'm going to talk about with these is like here on the second page. So
I will take it.
Sorry. I thought I heard it, but yeah.
Yeah, no, well, she didn't.
Oh, okay. Okay, so it's heating up, right? Now, what I was saying is this, like on the second page here, like this stuff, some of this stuff it's talking about things over here. So just so you know, there is information on this page about those diagrams. Okay, now, so as a solid, it's heating up, right? Now we just talked about the two things that can happen to the molecules while phase change are occurring, right? They can get further apart or closer together, or they can speed up or slow down. Everybody's good on that, right? Now, in general, we typically talk about those things as kind of like happening together, like in the other set of notes. Like basically, we think of it like as you get more energy, they move faster and spread out, or whatever. Or as you lose energy, they move slower and get closer together. So we kind of generalize them together, but in reality, those two things don't happen at the same time. They don't move faster or slower and get closer or further apart at the same time. It's typically one or the other. So on this, while this is a solid, the temperature is increasing. Anybody remember what causes the temperature in a substance to increase? Like adding energy, right? But what's happening to the molecules that causes the absorbing heat and makes them, say it again? So the friction from it, right? And then I think I heard somebody else say speed up, right? Yeah, good. So the friction, and if you're getting more friction, it's because they're moving faster, right? So at this point, when the temperature is changing, the speed of the molecule is changing, but not the distance between them. Okay, I'll say that once again. When the temperature is changing, the energy that's being added is making the molecules move faster. or if it's being taken away, it's making it move slower. But the distance between the molecules is not changing, okay? Now, we get to this point here, solid/liquid with B. That's represented by this part of the line, this straight part there. This is the time when the actual phase change is happening. The solid is turning into the liquid. Okay? The actual phase change is occurring. But if we look at the graph, what does the straight line tell us about the temperature? Yeah, good. It's staying the same, right? Like the temp at this point isn't changing. It's turning from a solid to a liquid, but the temp is staying the same. So this point right here, the point at where it turns from a solid to a liquid, the temperature point for that is called the melting or freezing point, right? Oops, sorry. So like that point on the temperature scale would be the melting or freezing point. Okay, so let's think about like kind of like real life concept. You have a glass of ice, you have water in a glass, you have a bunch of ice in there, so you have ice water, right? Now obviously when you first put it in there, it has to kind of even out temperature wise or whatever. But after a few minutes it kind of evens out or whatever. What temperature is the ice water? Anybody know? Oh, sorry. Nope. Not yet. I mean, eventually a long time, but when it's ice water, it would be. Okay. 32 degrees. Why? There you go. 32 degrees Fahrenheit, 0 degrees Celsius. The whole time. Ice water would be 32 degrees, 0 degrees Celsius. Until what happens? Bingo, good. When all the ice melts, then the phase change is complete. Like I know that you like put water and ice together separately, but like once it's in the cup together, you can think of it as all one thing. It's all H2O, and it's partially between liquid and solid forms, right? And it's going from solid to liquid. So it's in the middle of a phase change. The temperature stays the same until the phase change is complete. The phase change is complete when all the ice is gone and everything's liquid. So, over here, like it says, during a phase change, and this is the thing that can trip people up or seems weird. During a phase change, the temperature of the substance does not change. However, during a phase change, the energy of the substance changes, either gained or lost. So, the weird thing is, it's still gaining, so on a heating curve, for what we have here, it's still gaining energy, but the temperature is not changing. Anybody know where that energy is going? Go ahead, guys.
So, say the ice and the water is in the same cup, but also in a room.
Mm-hmm.
The ice never melts. Would the room have to be 32 degrees also?
Yeah. If for it to not, yeah.
Well, then what if the ice freezes? Or like the water freezes?
Well, that would only happen if what?
It gets colder.
What's that?
It gets colder.
Right, which would have to suggest that the air around it or whatever would have to be colder. So like, say for example, you had a glass of ice water and you put it in the freezer. Eventually the whole thing would freeze, right? And that's because the air, it's trying to equal out the energy, but the air around it is so much colder that it's pulling heat out of the ice water, and it would pull enough out eventually that it would all turn to a solid. But yeah, if you were like, say you had your refrigerator, like you can adjust the thermostat setting on something. Say you had it like right at 32, and you put a glass of ice water in the refrigerator. It's possible that it would just stay ice water the whole time, not frozen or solid, like it would just stay in between because it's at the same temp. So, it's not very likely because it'd be really hard to keep something right at that point. But yeah, I mean, concept wise, yeah, it's possible. So, okay, so back to the question though for this. If during the phase change it's gaining energy, but the temperature is not changing, where's that energy going? Or what is it doing?
Trying to get into the rest of the solid.
What's that?
It's going to the rest of the solid.
Yeah, it's going to the rest of the solid. And what's it doing? So what two things change about molecules during phase change, like when we're talking about phase change stuff? We said, what two things?
Speed,
Speed and
distance.
distance between, right? If it's heating up, or if the temperature is changing, we said that tells us that what's happening. The molecules are changing speed, going faster or slower, right? So temperature change means change in speed, which means if the temperature's not changing, it means the speeds are staying the same.
Change.
Bingo. Which means if the energy is still being added, the thing that has to be changing is the distance between the molecules. Okay, I'll say that again. During a phase change, the temperature does not change, but energy is still being added if we're going on a heating one, or it'd be taken away if it was on a cooling one. The energy changes. That energy is being used to pull the molecules further apart, or if it's losing energy, it causes the molecules to go closer together. To go back to the magnet example, if you got two magnets that are together, they're decently strong magnets, you have to actually use some energy to pull them apart, right? Like you have to actually kind of use some energy to get them apart. Well, that's what's happening in the phase change. During the phase change, the energy, it's not going to make them fast. It's not being used to make them faster. It's being used to break those intermolecular bonds and move the molecules further apart. Which is why the temp doesn't change. Does that make sense? It's kind of weird, but okay. So temperature change, no temperature change, but still adding energy. So if we're going from a solid to a liquid, if we're going this way, which is that going to be, melting or freezing? Melting, good. So this one is melting. It'd be freezing if it was going downwards. Then we get here. This part of the line represents the substance as a liquid. So what's happening along that part of the line?
Heating up.
Heating up, temperature's changing, which means what's happening to the molecules? Good. Going faster, right? Then we get here to part D. There's supposed to be a slash here. This is not liquid gas. It is liquid slash gas. This part of the line is the phase change from a liquid to a gas. Okay, that's called vaporization, going that direction. Okay. Temperature not changing, so what's happening to the molecules during this part? Good, further apart, yes. Last part here, it's all turned into a gas, so the temperature is changing, so the molecules are getting, there we go, good, getting faster. Okay, make sense?
Yes.
Any questions? Okay, cooling curve is essentially the same thing. It's just going the opposite direction. It's losing energy and the stuff's going down. Okay, now, the one thing on the cooling curve that we have here that's a little different is we've got this part right here. See this little bump? The divot? That is what's called supercooling. Okay? So supercooling is a condition where a liquid is cooled to a temperature below its freezing point without turning into a solid. Okay? This happens when there is a lack of a crystallization point within a liquid. So, first of all, I'm trying to think of how to, like, so we know that, like, from a liquid to a solid, the molecules slow down. They slow down and they're kind of like closer together and stuff, right? But in general, the molecules in a liquid are really close, or they're pretty close already. So does anybody know what kind of the main difference in terms of how the molecules move, what the main difference between a liquid and a gas is? Or I mean, a liquid and a solid?
Liquid molecules move in freely.
Okay.
Solid molecules that are kind of condensed in one space.
Yeah, good. So they're both really pretty close together. But so kind of think about like in a regular year, like our hallways, right? Like there's so many people in them or whatever, but everybody's constantly moving. So there's not a lot of space in between, but people are constantly flowing and moving past each other. It's kind of like molecules in a liquid, okay? But in a solid, the molecules kind of get almost quote unquote frozen in place. They get kind of locked in place and they don't switch past each other and stuff like that. Okay, this being locked in place, if it forms like a repeating pattern, that's called like a crystal structure. And all crystal structure means it's kind of like a repeating pattern, and that's what a lot of times what solids have to them. Okay, so, but what has to happen is when you're going from a liquid to a solid, a lot of times you have to have what's called a crystallization point or a crystallization event. And that's essentially something that allows that repeating pattern and allows those molecules to start falling into that repeating pattern. Let me give you some kind of example, like real life type of idea. When water condenses, turns from a gas to a liquid. So like say, think about like you take a hot shower, right? And you get water condensing in the bathroom. Where does the water condense? Like where do you see condensation?
The mirrors.
Yeah, like the mirrors, sometimes even like the walls or whatever, but like that, right? Mirror stuff. You get dew forming in the morning or whatever. Where's the dew? Yeah, the grass, the ground, cars, whatever, right? You get frost forming from water vapor in the air directly to a solid. Where does the frost form? There you go. All things have in common is they all form on a surface. A solid surface or something solid. That solid object or surface or whatever it is acting as a crystallization point. It's acting as the thing that kind of starts, so then they can either condense as a gas or start to crystallize as a solid. So it needs some kind of a surface or point. Now here's the weird one. Think about rain. Rain is water turning from a gas, water vapor, into a liquid, correct? How does it happen in the middle of the air if you need some kind of a surface for it to condense? Well, temperature can lead to it, but that's not actually what allows it to happen. Well, I mean, it is part of it, but there's another factor.
The molecules in the air combine together.
Yeah, you've got the right idea, really close. So the molecules getting close together, but the thing that like kind of like kicks it off that allows it to actually start condensing, every raindrop starts by forming around a tiny speck of dust or dirt or something like that in the air. there's like tiny solid little, dust particles and stuff in the air constantly. That's what rain starts to form around. The first water molecules that start condensing around a tiny solid dust particle. And then once it started, all the other water molecules can condense because it's kind of like kicked it off. It's like a chain reaction, right? So they can start condensing. And then eventually, there's enough of them that condense into liquid, it gets too heavy and it falls, and that's rain. But all raindrops and stuff have like a tiny piece of dust that started it. Okay? Now, there's cases where you can actually get, like in the case of water or something, you can cool something below the freezing point, but it's still a liquid and it doesn't turn into a solid. So you can get water colder than 32 degrees Fahrenheit, 0 degrees Celsius, and it still is liquid. Because that only occurs if it's like really pure and there's a real lack of crystallization points. That's called supercooling. Okay, later on this week, I'm gonna try to show you an activity, like a demo with that, and kind of look at it. But that's called supercooling. But then once the crystallization starts, once something triggers that, and it starts to crystallize, then it goes to the freezing point. Boom. So basically, what I want you guys to do is like if you see that bump, I want you to understand that that's a supercooling event. If you see like a little like divot like that in a cooling curve. Okay, now you can actually have the same thing going the opposite way. You can superheat water. Superheating water is where you heat liquid water past the boiling point, but it doesn't boil. You make the water hotter than 100 degrees Celsius, or what is it, 212 or whatever Fahrenheit. You make it hotter than that, but it stays water. And I'll try to show you guys a video of this later this week if we have a little time. The Mythbusters did like a little thing on this because there was talking about it going around where water kind of quote unquote exploding in people's faces after they heat it in the microwave. They tried it out and it works. You can, if you have like really pure water and you can heat it in the microwave, you can heat it past the boiling point. You can heat it past the boiling point, it doesn't boil. But the danger part comes in is, so it's basically the same thing as the supercooling. There's no like event that's triggering it to like triggering the molecules to kind of like I'm trying to think of how to do this, like say this, like it's almost like they have to get kicked off, like the first ones have to then turn into a gas and then they all start to do it. But if there's a lack of things to allow that to happen, you can heat it past the boiling point. The real dangerous thing about that is, as soon as something is introduced, a event to do it, because all the water is heated past the boiling point, all of it tries to instantly boil. So like they do it and then they like dropped a fork into the water that was superheated, and the whole thing like explodes. It not explodes like a bomb explodes. It's like like the water all over the place, like superheated water. And it's because once that fork or that item hits it, it instantly triggers the phase change. But because all the water is superheated, it all tries to boil all at once. So you just basically get this big cup of water that's super, super crazy hot, and it all tries to boil at once and just all over the place. So some people were actually getting really severe burns on their face and on arms and stuff like that if it happened to them. But so what that would look like on a graph, like that would look like this. The superheating event would look like that. So it would look like this, like where it's a liquid, and then it would bump above the vaporization point, like that, and then once it started, it would come back down and hit it. So it's kind of the reverse of the supercooling. Okay, makes sense. All right. Any question about the supercooling, superheating? Let's see.